Hello, everyone. This is Wenyuan Wang. You can also call me Mike. I'm currently a research assistant professor at the University of Hong Kong in the group of Professor Hoi-Kwong. It is my honor to come here to QCrypt and present our work. My topic today will be fully passive quantum key distribution. As an outline, I'm going to first introduce the motivation of the project. So why do we want passive QKD in the first place? I'm going to then introduce the existing works, including passive decoy and passive encoding. I'm going to then introduce our design of a fully passive source that's capable of creating arbitrary polarizations and arbitrary intensities of a coherent state. I'm going to then introduce how do we make use of that passive source to create fully passive QKD protocols. That includes a set of post-selection strategy, that includes a tweaked decoy state analysis, and also finally, how do we prove the security with mixed polarizations for the signal states. I'm going to then show with numerical simulation results that we can get satisfactory key rate with our new proposal. And lastly, I'm going to show some proof of principle experimental demonstrations that shows the validity of our experimental assumptions and that passive QKD is indeed possible to implement with an experimental setup. So let us begin. So first, for the motivation. We know that usually QKD systems will involve active modulation devices, such as intensity or polarization modulators. And these modulators might actually introduce side channels, such as the correlation of intensities between neighboring pulses. And also they might be susceptible to hacking attempts like Trojan horse attacks. So it would be highly preferable if we can actually only use post-selection to obtain the states we want, such as the decoy intensity settings, or even the polarization or the phase that actually encodes the key bit that doesn't use any active modulators. In that way, you're actually not susceptible to any side channels in the source modulators. Note that, of course, those random bits don't come from thin air, so we still need to secure a source of randomness, which is usually the random faces of the laser pulses that are inaccessible to Eve. And now let us introduce the existing work. So the idea of passive decoy state was first proposed in 2009. And the idea is that if you interfere two-phase randomized coherent lights, the output of those two ports would actually be correlated. So if you actually observe one of the port and post-select upon your results, you'd actually conditionally decide what are the distributions on the other port. Now, this can be done with single photon detectors or with classical photodiodes. And in this presentation, we'll actually focus on the classical case, where the source 1 and source 2 are strong lights. And after they interfere, if you look at the intensity of one of the photodiodes, because the total intensity is fixed, then you can know for certain what is the actual intensity on the other port. And before outputting, you can use an attenuator or a beam splitter to attenuate it to single photon level for QKD use. And if you have two-phase randomized inputs, the output distribution of the intensity would actually look like this, like a U shape. Let's remember this as we'll actually repeatedly come to this plot later on. And by the post-selection, we can actually define this post-selection threshold and divide the signals into the upper portion, the lower portion, into those two bins. And in fact, the signals in those two bins would have different average photon number distributions. So you have two distributions that you can use to construct two linear equations, and you can feed it into a linear program solver and perform decoy state analysis. So that's the idea of passive decoy state. And a very similar setup is actually passive encoding BB84, where instead of sending signals in the same mode, we actually have H and V polarizations on the two arms. And because those two arms actually have a random phase between them, we're actually creating states on the equator of the Bloch sphere. And of course, Alice can actually, again, split off that classical signal and measure the phase. And depending on her measurement, she can actually perform post-selection and select the 4 slices of LR and plus and minus states, which can be used for BB84. So far, there have been several successful experimental demonstrations of passive decoys. And other interesting setup include passive continuous variable QKD and also electrically modulated BB84 that doesn't use any optical modulators. There have also been, notably, a protocol for passive encoding and decoy state preparation, but it actually uses a nonlinear optical effects as one of the key components. So our work here will actually focus on DVQKD, and we will propose to do all the encoding and decoy setting that are generated by post-selection only without any modulators. And more importantly, we also only use linear optical components that make experimental implementation a lot easier. So what is actually the challenge here? For over a decade, you see that since the proposal of the passive decoys, there has never really been a successful combination of passive decoy and encoding for such a fully passive scheme with only linear optical components. The reason, we think, is because of the correlation between the polarization and the intensities. So it can be actually split into two different factors. The first one is there's not enough degrees of freedom in the source. Remember, in those setups, we only have 2 lasers, right? And those 2 lasers are actually just not enough to describe independently the intensity, the polarization, and the global phase. And second, second is a little bit more subtle, is that Alice actually pulse selects over a finite region of different intensities and polarizations. And in those regions, there could be correlations between the polarization and intensity distributions. And as we'll later show, this correlation actually makes a decoy state analysis very difficult. So our solution to those two problems, one, we actually propose a fully passive source with 4 lasers. So we have 4 independent DOFs that are capable of preparing independently a state with arbitrary intensity and arbitrary polarization, and also one more DOF that's remained for the global phase randomization. And also, we actually construct a set of nice post-selection strategies that actually shape the distributions and make them decoupled along the polarization and intensity directions. Therefore, we can allow standard decoy state analysis. So let us first introduce our setup of the source. So the source actually looks like this. We have 4 independent lasers, and each one of them has a random phase, phi 1 through phi 4. And the first 2 pairs of the lasers with edge polarization are interfering kind of like a passive decoy setup. And of course, the bottom 2 lasers are also interfering in a passive decoy setup as well. And as we learned from the passive decoy, the output from those interference of 2 random phase lasers would actually be this U-shaped distribution for the mu. So it would actually output this random mu edge and also a random phase phi edge. And similarly, this V arm would actually interfere and output a random mu V and also a random phi V. And those 2 random intensity and random phases would actually be combined at the PBS into the output. So the next question is, what is the output of the PBS? Well, it turns out that the output of the PBS will also be a phase randomized coherent state. Its intensity would actually be the sum of the 2 intensities for mu h and mu v, and its polarization is determined jointly by the theta and phi, which is actually the polar angle and the azimuthal angle on the Bloch sphere. And the theta is actually determined by the ratio or the asymmetry of the mu h and mu v, and phi is actually determined by the phase difference between the h and v arms. We can also write it out in terms of the Poissonian state and also the creation operators for that coherent state. So we can actually prove that each one of the mu h and mu v and also phi h v, each one of those sets that Alice observes corresponds to a state on the Bloch sphere. And we can even prove the inverse is that any desired polarization on the Bloch sphere and any intensity that Alice wants can also be mapped back to find a set of mu h, mu v, and phi h v that creates it. So with this equivalent like conversion relationship, we can see that we have a fully passive source that's capable of creating any state with arbitrary intensity and polarization that Alice wants, as well as on top of that, a global phase randomization. But of course, we know that up to this point, we haven't really mentioned the post-selection strategy yet, because the source itself, we stress, is protocol independent. And we only later define this map of, let's say, mu h and mu v, and define the regions that we post-select on that map, which actually corresponds to the state that Alice actually wants to prepare. So in the next slides, we actually introduce what kind of post-selection strategies do we use to define the states for Alice. So let us actually go into the section on fully passive QKD protocols. So here, we actually define regions that corresponds to the 6 states, HV plus minus and LR, in the 3 bases of X, Y, and Z. And note that these are not the only states that Alice can prepare. Again, our source is a general purpose source. However, we chose these states because they can actually be used in popular protocols like BB84, RFI QKD, 6-state, and even in principle, MDI QKD. So if we look at the plot here, this is actually how we define the post-selection. We can see, for instance, this little region here actually corresponds to the H state because it has a strong mu H intensity and a close to 0 mu V intensity. And that also corresponds to the north pole on the Bloch sphere. However, because the mu V is never strictly 0, we see that it's not a perfect H state, but actually has a little bit of a wiggle room on it. So we define this solid angle on the north pole, which corresponds to your H state. And vice versa, we also have this V state where you have a strong mu V and a weak mu H. And also in the cases where mu H and mu V are roughly equal, you end up with the states on the equator of the Bloch sphere. And Alice can actually further post-select upon the face to actually determine the plus, minus, L, and R states. And we can also, of course, define them by a set of mathematical parameters, including the max intensity, the slice sizes for each one of those post-selection slices, and also 2 additional thresholds where we can actually cut each one of those states into further subregions that actually corresponds to different levels, like the strong intensity versus weak intensity for your decoy settings in that one particular polarization. And on top of this post-selection region technique, we actually can have an additional tool for Alice that's actually very powerful and useful, as we'll show here. So Alice can actually perform not only a post-selection on the intensity itself, but also post-selection on the probability distribution of her signals. So we can think of it like this. Alice actually holds a biased coin, and the weight of the coin actually follows a distribution of this Q that's a function of mu h and mu v and phi hv. So depending on what Alice actually observes, she actually throws a different coin, and depending on the result of the coin flip, she actually decides to keep or discard that signal. So in that way, she can actually compensate the overall distribution of the signals, and in a way almost actively modulate the distribution to her will. For instance, if you start off with a non-uniform phase distribution, she can actually throw more signals in the 0 end and keep more signals more likely on the 2 pi end. In that way, after this compensation, you end up with a uniform distribution. And similarly, if we have that U-shaped distribution for your intensity, she can also discard more signals on the 2 ends to end up with, let's say, a uniform distribution, or actually any other distribution that she wants. This, as we'll later show, is actually very important for our decoy state analysis because it allows us to shape the distribution and then decouple the polarization and the intensities. So at this point, the cards are all on the table, right? We have defined the passive QKD protocols. However, we actually still have 2 remaining questions. One is that because of those post-selection regions, we have WCP signals that have mixed and actually correlated polarizations and intensities. So how do we use them to calculate the bounds on the single photon statistics? So how do we perform the decoy state analysis? The other question is, for the single photon components, those signals will also have mixed polarizations. And is it still secure to use those signal states that have mixed, basically imperfect polarizations? And that's the second question we have to answer. So we'll answer them one by one. First, for the decoy state analysis. So if we look at the active QKD case, Alice usually selects a set of discrete intensities like mu1, mu2, and mu3. And your observables would actually be this combination of different n photon contributions times the probability of choosing those n photons, basically a Poissonian distribution. And similarly, for passive QKD, we'll also define different regions as the decoy settings, like S1, S2, and S3 that are defined over this mu h, mu v, and phi hv that Alice actually observes. So as we can see here, there's actually a problem because if you define a region that's like a sector shape here, then we can see that the theta, the polarization, is a function of mu v over mu h, which is actually the slope of that line. And over that region, that slope can actually take different values. So it has a little bit of a wiggle room there, which actually means that this polarization would actually follow a polar distribution for your decoy setting. And that actually means the average of the yield would actually depend on that one polarization distribution. So for an n photon pulse, like a Fox state, its statistics would actually not depend on the intensity because a Fox state doesn't contain any information of the coherent state. However, this Yn and also the En, the QBR and the yield, would actually depend on the polarization that you're preparing the state in. So that means if your polarization has a little bit of a wiggle room, it would actually depend on the mu h and mu v regions that you define. And similarly, the Poissonian distribution, this Pn, also depends on your mu h and mu v, which means this integrand is a function of mu h and mu v. You can't decouple them into these separate integrands of Pn's average times Yn's average. So you can't really construct a linear program anymore because you can't have a consistent set of Yn, average Yn, over all decoy settings. Physically, this is actually understandable because, as we said, the average of Yn depends on the decoy setting. And incidentally, for each one of the decoy setting, they might actually have a different polar distribution, which means the average of Yn would actually be different. And if they're different, of course, you don't have a consistent set of variables for each one of the linear equations, then you can't construct a linear program anymore. So how do we solve this problem? Well, the idea is surprisingly simple. We just use post-selection to shape those distributions and make the polar distributions identical for each one of the passive like decoy settings, and therefore enabling decoy state analysis. So how are we going to actually do this? Well, to start, we actually describe it in terms of the polar coordinates. So instead of using mu h and mu v, we actually start with using r and theta. Note that the theta is not exactly the polarization, but actually has a one-to-one correspondence with the polarization angle, so we might as well call it just the polarization. So if we look at the integrand in terms of the polar coordinate, we see that it actually consists of 4 different terms. This is the actual intensity probability distribution. This is the Poissonian distribution for the photon numbers, and this is the Yn, which is actually the photon number yield, and r that comes from the coordinate change. So if we look at the Poissonian distribution, we see that it actually contains 2 different parts, an exponential part times this polynomial part. So the idea is that if somehow we can magically find this special intensity distribution that takes this exponential form, it will actually cancel out with the exponential form in the Poissonian distribution, and we'll end up with a very beautiful form for that integrand, which is simply a decoupled product between the radial portion and also the angular portion. And in fact, we can do this because, again, as we remember, Alice has that coin flip post-selection method, right? So she can actually shape this distribution, which start off from a U shape, into this exponential shape that we like. So in that way, you can actually decouple the integral. And on top of this, actually one more thing we need to mention is that we also need to choose a square region for the r and the theta, from r min to r max, theta min to theta max. But in fact, we can also do this by describing those sector shapes on the actual mu h and mu v maps. So once we have those sector regions, and once we have this post-selected distribution, we can successfully decouple that entire integral into two parts, the radial part and the angular part. The radial part actually corresponds to the new photon number distribution, and the angular part is the new variable for the linear equations, which we actually call the pseudo yield. So the pseudo yield is actually a setting invariant term. This is actually because by using the post-selection and choosing the sector shape regions, we have forced the same angular distribution for all decoy settings. So right now, of course, the integral or the average of the yn has to be the same across all the decoy settings, which is this new variable pseudo yield that we can use for the linear program. So now the linear programs can be constructed as usual, and we can just feed it into a solver to solve for the upper and the lower bounds for the yn prime and also the en yn prime. And on top of that, we can also prove that those bounds that we get on those pseudo yields are also bounds for the perfectly encoded single photons. So this means that had Alice actually sent pure states, those HV plus and minus, without any without any mixture in the polarization, then the statistics for those perfect states can also be bounded by whatever bound you get from this linear program. So once you get those values from the linear program, you can just feed it into the security analysis and calculate the amount of privacy applications you needed. So now we already have the bounds on the perfect single photon statistics from the decoy analysis. Question is, how do we treat the security? So here for the signal states, we only need to consider the single photon component. So we can think of Alice as following a virtual single photon based BB84 protocol. In this protocol, she will actually encode perfectly encoded single photons in the X spaces and actually send single photons with imperfect mixed polarizations like this 3D solid angle in the Z basis. And this is actually because, again, from the decoy state, we already know the bounds on the perfect single photon statistics. So we can think of the test states as perfectly encoded single photons. But the question is, with those mixed polarizations in your Z basis, is the private simplification still in the same form? So can you still use the single photon perfect statistics as the private simplification? Or in other words, the bit error rate that you get for the X spaces single photons, is it still the phase error rate for the signal states despite the mixture and the polarizations? Well, the short answer is yes. But to show our reasoning, let us actually look at a different picture. So we consider the equivalent entanglement distribution picture, where Alice and Bob are actually both defining POVMs to actually measure the incoming EPR pairs. In that way, the imperfect preparation in the Z basis in the prepare and measurement picture can be thought of as imperfect Z measurements in the entanglement distribution picture. So instead of preparing different Z states, you can think of Alice as making Z measurements, and those measurements themselves actually have a little bit of a wiggle room over your 3D solid angle. And we prove that given that the integral regions, those SH and the SV, are symmetric, which in our case they are, we can actually write this integral over that region as just the mixture between a perfect measurement along the Z basis plus some proportion of this random noise. This is an identity matrix. Like it corresponds to a fully mixed state. So this is just a random post-processing noise on the 0 and 1 bits for the Z basis. So this means that the imperfect preparation of the states is equivalent to a random post-processing noise. And of course, such a classical post-processing noise will not increase Eve's information, so we're secure to use the same private simplification term as if they're perfectly encoded signal photons. In fact, this is similar to an adding noise protocol, which suggests that we might be able to further decrease Eve's information because of Alice's classical post-processing noise, but we'll leave that as a subject of future work. So now let's actually look at the performance of the protocol with some simulations. So here we actually plot out a simulation of the 3 decoy setting passive QKD protocol versus the active QKD counterpart. And as we can see here, it has consistently a good Q rate across all distances, but it has about 1 order of magnitude lower Q rate than the active QKD. That is actually because of the sifting and also the inherent QBR of the finite polarization slices in the key generation basis, which is the price you have to pay in exchange for the better implementation security of passive QKD. And we also show it for the finite size case with collective attacks. And as we can see here, even with Alice doing a lot of post-selection and also shaping the intensity to her likes, we still have acceptable key rate, even with like relatively smaller data sizes, like 10 to the power of 10. And lastly, we also tried it with RFI QKD for the asymptotic case. We fixed the distance and then scanned it across different misalignment angles. As we can see here, the reference frame independence can still be attained even with a passive source. Although, again, we lose about 1 order of magnitude of key rate because of the shifting NEQ and QBR in the Z basis. And lastly, there are some experimental assumptions we're making. So first, we actually require Alice to have uniform and independent phase randomizations between the pulses. And we also require Alice to be able to perform accurate and fast classical intensity and phase measurement. And lastly, Alice also has to maintain good interference visibility between her lasers, between all of those 4 independent lasers. Actually, for that last part, we have a different proposal. So we propose an alternative 1 laser experimental setup where basically 1 laser is combined with just delay lines. Therefore, a pulse train is actually delayed and basically time multiplies, and 4 signals are actually interfering together from the same pulse train. In that way, we're reducing the clock rate to 1/4 of the original value, but we can avoid the frequency mismatching problem because all of those pulses actually come from the same source. Note that here we need an intensity modulator or an optical switch to suppress every 3 and 4 signals. But because this pattern is actually just a fixed pattern, we're not leaking any additional information to Eve. In fact, we performed a proof of principle experimental demonstration to show the validity of those assumptions we make on the experimental system. This part is actually led by Dr. Chen-Jiu Hu, who is actually the experimental postdoc in the group of HKU. So first, we actually test for the passive decoy-state module, where a gain switch laser actually outputs pulses. And those pulses can actually be phase randomized and also uniformly randomized. And that pulse train is actually divided equally into 2 paths and delayed, which means the pulses are actually interfering with the neighboring pulses from the same train. After interference, we actually measured with a high bandwidth photodiode and look at the intensity distribution. As we show here, that intensity distribution follows that U-shaped distribution as we expected. So this actually means that there's good uniformness of the distribution of the phases and also good interference visibility of our sources. We also show a histogram of the simulated data, and as we can see, the experimental one actually follows it very well. We also tested the autocorrelation of the output intensity sequence, and we see that the average autocorrelation coefficient is within the expected range of the theory value for a truly random string, which means that not only do we have uniformness, we also have randomness of the phases. Next, we also tested the passive encoding module, where for simplicity, we're not combining it in concatenation with a passive decoy, but rather we're just using 1 pulse train divided into 2 equal parts, and then again, delaying and interfering. So in this way, we're having equal intensities for H and V, and we're just creating states on the equator of the Bloch sphere. And then we actually measure it in 2 different bases, which are actually aligned to the X and the Y bases. Now, looking at the intensity of each one of the detector, you can actually deduce what is the original phi here. And because you have 2 pairs of bases, you can actually have 2 values of theta, and you can basically compare the theta to see if you actually got it right. And the difference in the measurement results would actually correspond to a measurement of your basically detector error or the misalignment error in your detection system. So here we actually plot out the results. As we can see, the measured phases actually range pretty well from 0 to 2 pi. We can graphically show it on the Bloch sphere as well, and you can see it nicely occupies the entire equator of the Bloch sphere, which means we are generating those states around the Bloch sphere randomly. And moreover, we can also see the error, which is actually the error between your X and Y bases, is average about 0.2 radian, which means you have good alignment for your measurements. And lastly, we also test the long-term stability for your passive encoding module. Here, we actually turn off the path delay, so there's no random phase between the pulses, and we are basically just preparing H plus V all the time. And that state is slowly drifting over time. We measure it over 20 hours, and we see that the average phase drift is about 0.4 radian per hour, which is actually very slow. And basically it means that this drift is negligible within 1 pulse or between neighboring pulses. We also see the average measurement error between the DA and LR results is below about 0.1 radian. Note that there are some peaks in the error that actually corresponds to the peaks in those sinusoidal waves. In those regions, it's actually sensitive to the intensity, accuracy, and also fluctuations. But of course, you also have a different basis that's on like a linear region, so you can always pick the better theta results among the 2. So overall, with the proof of principle test results, we show the uniformness and also the randomness of our phase distribution. We also show that we can perform accurate and stable intensity measurement as well as phase measurement. As a conclusion, we have shown that we can construct a fully passive general purpose source that can arbitrarily create any polarization and any intensity. We designed a set of post-selection strategy to enable passive BB84 and passive RFI QKD. We have also shown some tricks to enable decoy-state analysis, and also we argue that the security analysis still holds true even if there is mixed polarizations in your single photon states. We show with simulation that you can get satisfactory key rate, although it's about 1 order of magnitude lower, in exchange, of course, for the removal of modulator side channels and better implementation security. And lastly, we show with proof of principle experimental demonstration that in fact, we can actually have validity in our experimental assumptions, and it's possible to implement this passive QKD system. And lastly, there is an alternative approach that actually uses a different decoy-state analysis and a security proof. And if you're interested, do please kindly check it out too. It's one of the posters, and the preprint is also coming up on arXiv very soon. So thank you very much for listening.